Hello ladies and gentlemen, this is Math, the language of science, and correlates with Chapter 2.2 in your textbook. Key vocabulary for this video are accuracy, precision, significant figures, and anomalous data. You also have mean, median, mode, range, estimate, and scientific notation. These are words you should know from math. If you don't, or if you need extra practice, please see page 55, 58, and 59 in your textbook. Precision versus accuracy. Precision is how close the numbers are to each other. Tight grouping of results. For example, these numbers are all within 0.1 to 0.2 millimeters of each other. They're very precise. Visually, if you look at the red dots, they're all tightly grouped together. They're very close. Those red dots are very precise. Looking at the blue dots, they're not as close as the red dots, but they're still relatively close, making them still precise. Then you've got the green dots, which are even further apart, so they're starting to become imprecise or not precise. But they're still pretty much in the same quadrant, so depending on your tool, some might consider them still precise. Accuracy is how close your measurement is to the actual value. Accuracy uses averages. For example, if the actual measurement is 13.5, and you measure 13.5, 13.6, and 13.4, the average of those three data points is right on target, making your measurements accurate. There are two ways to be accurate. The blue dots in the square show very good precision because they're close together, and they're right on target. They're right on that X which we're aiming for. However, these red dots are also accurate because remember, accuracy uses the average. So if I were to average these four data points, the point where they intersect is right on the X, making these measurements very accurate. I find this chart a helpful way to visualize precision and accuracy. It is possible to be neither precise nor accurate, which is our top left, precise but not accurate, top right, accurate but not precise, bottom left, and precise and accurate, which is our bottom right. If this chart is helpful for you, I would copy it down in your notes. Anomalous data is data that doesn't fit with the rest of the data. If you look at the applied on page 59 in your textbook, you can see a data table of female black bear masses. Looking at the data, all of it's within the 70 kilogram range, except for one, bear D. This is an anomalous data point, most likely caused from the researcher measuring in pounds, not kilograms. It needs to be thrown out before analyzing your data, otherwise it will skew or mess up your results. You might remember learning about outliers in science last year. An outlier is an anomalous data point in a graph. In a data table, it's called anomalous data. Significant figures, also called sig figs. They'll tell you two things. One, what the measurement for sure was, and two, the precision of the tool used to get that number. This is easier to understand with an example. Here we have a ruler measuring centimeters. We can see that the box is definitely at least 3 centimeters long, but we also can see that the box goes beyond that. We don't know for sure how far because our tool is not that detailed, but we can estimate it. For this, I'll estimate it at 0.5. So my measurement that I write down is 3.5 centimeters, which is 2 significant figures. Another scientist looking at this measurement in a lab report would be able to know that I knew for sure the box was at least 3 centimeters long, and that I estimated the second digit because my tool only measured centimeters. Let's say I get a better tool, one that measures millimeters, and I measure again. This time, I know that it's at least 3.4 centimeters, but it goes a bit beyond that 0.4, so I would write my measurement as 3.45 centimeters, which is 3 significant figures. The other scientists knew that I had a tool that measured 0.1 centimeters, and that I knew for sure it was at least 3.4 centimeters long. I get an even better tool. This one measures to the 0.05 centimeter. Looking at the box, I can see that it's 3.45 centimeters long, and that it looks like it's exactly on that 0.05 mark. So I would write my data as 3.450 centimeters, which is 4 significant figures. That 0 on the end lets other scientists know that I knew for sure that the box was at least 3.45 centimeters, and that I didn't just estimate that last digit. In general, the more precise your tools, the more significant figures your measurements will have. Counting sig figs. There are a few rules for counting sig figs. This chart details the major ones. Be sure you copy this down in your notes and that it makes sense to you. If it doesn't, write down some questions and I can help you in class. Lastly, there are 2 rules to remember when working with numbers in science. When you are adding or subtracting numbers together, whichever number has the least number of sig figs after the decimal place is the number of significant figures you need in your answer. For example, 45.1 has 1 sig fig after the decimal place. 3.14159 has 5 significant figures after the decimal place. Your answer needs to have 1 significant figure behind the decimal because it needs the one with the least number of sig figs after the decimal place. When multiplying, the answer needs to match the number with the least total number of significant figures. For example, 2 has 1 significant figure. 4.206 has 4 significant figures. When I multiply them together, the answer can only have 1 significant figure in it. So while mathematically we get 8.412, we have to round our answer to 8, so we only have 1 significant figure in our numbers. All done! Make sure you know and can use all the key vocabulary, can explain the difference between accuracy and precision, are able to identify the number of significant figures, and know how many significant figures you need to have after doing a calculation.